Can everyone hear me? Yes? Okay, very good. So let me start off by thanking Avia and Claire for inviting me here because I've already learned a lot by being here and I hope to learn more in the coming days. And it's also been very nice to meet with old friends like André Varlamont, who spent too little time together over the years. But whenever we meet, it feels like knowing each other forever. And also make a lot of new friends. So thank you very much for that. So that's the talk I want to give today. So today's lecture is, and Q&A is going to be on Superconductor-Insulator Transitions in 2D. And this is old work, as you'll see that actually I worked on this for a period of 20 years. But when I was making these slides, I realized that I haven't thought about this problem in the last 10 years. So I had to read my own papers. Unfortunately, this old work has aged well, like mine. So I'm happy to talk about it. But I have not kept up with the experimental developments. So please, there are a lot of experts here who can tell me. Okay, thank you. Thank you. So I may be very often experimental. Then my lecture tomorrow is on a completely different topic. And since theorems were already debunked, today I'll be presenting mostly numerical work, but tomorrow I'll present you rigorous inequalities valid under certain conditions. Okay. So I'm going to talk about other upper bounds to superconducting C, focusing on 2 dimensions. And here are some papers on that. Actually, the theorists here seem to care a lot about topology. So today's lecture will be topologically trivial, even if physically non-trivial. But tomorrow's lecture will definitely have things like quantum geometry, Fubini's 2D metrics, Chern numbers, and so on. Okay. And then on Monday, so it's going in time actually. You can see what is evolving in front of your eyes. Monday, I will actually present a seminar on work we posted 2 weeks ago. So that's on the pairing symmetry of Morley graphene superconductors. There's plenty of topology in there. Okay, so here goes. So I think this talk this morning did a spectacular job of telling you about the experiments in the field of superconductor insulator transition in thin films. So here, let me just do a very quick summary that such transitions have been seen in bosonic systems, like Josephson junction. Okay, this is barely visible. Then Matthew Fisher proposed the Bose-Hubbard model, which was realized in the optical lattice experiments, which Marcus Linus did with Riemannian block. And they saw superfluid to Mott transition, which is a superconductor insulator transition. It's very beautiful work, but in field far removed from most people in the audience. But then there are lots of fermionic systems. And boson and fermion, I'm just saying that here there are no fermionic degrees of freedom. Here at least these systems have fermions where superconductor insulator transition is driven either by disorder or by magnetic field or by doping or by gating or by pressure. And so this is Alan Goldman's classic work, which Christoph described in some detail. This is Ivan Bozovich's work on tuning the superconductor insulator transition in LASPO. This is Pablo's work on magic angle twisted bilayer graphene, where superconductivity happens right next to a correlated insulator. So there's so many examples. So here is the original experiment on the superconductor insulator transition, where Alan Goldman's group, as a function of increasing disorder, which you can see they're decreasing the film thickness, what that's doing is changing the normal state sheet resistance. And for the less resistive samples, eventually they go superconducting. The more resistive samples eventually go insulating. And there seem to be a separatrix. And there are a host of 20th century experiments. And maybe I missed some important names here as well. Okay, so now a very brief history of the early theories of S-wave singlet superconductors with non-magnetic impurities. So again, it was described very well in previous talks that if you have weak disorder, so the elastic mean free path L is huge compared to the Fermi wavelength, then there's no effect of impurities on the thermodynamics and indeed on TC. That's Anderson's theorem, which Abrikosov told me was neither Anderson's nor a theorem. But Abrikosov and Gorkov had diagrammatic proofs of very similar ideas. So it's important that we have non-magnetic impurities on the potential scattering and you preserve time reversal. And then,
Mohit,
yes.
Allow me please to say 2 words. So I want to stress that Abrikosov and Gorkov received not only the statement that the non-magnetic impurities do not affect.
They also did magnetic impurities.
But they got expression for psi.
Yeah.
For psi in dirty systems.
Yes, square root. Yes.
Yes, and this is extremely important because previously Abrikosov found the expression for HC2.
Right.
That phi 0 divided 2 pi psi square.
Right.
So the fact that the psi square is psi 0 L means that you have the mean free path in denominator, and it was the rod how to increase second magnetic fields. So one of the obstacles of the application of superconductivity was resolved here.
Yes.
Sorry.
No, you're right. They did many other things. They also said what non-magnetic impurities do and how they would suppress. They got gapless superconductors, so on and so forth. But that's not a topic of mine. Then Finkelstein's work was also referred to. He put in this weak disorder, but Coulomb interactions, which renormalizes mu star, the effective attraction between fermions, excuse me. And this leads to a suppression of TC. And then when you get to a strong disorder, where KFL is a order 1, then all this diagrammatics just breaks down. Okay. And unfortunately, that is the regime where you see superconductor-insulator transitions. And you have Anderson fighting against himself, because weak disorder, Anderson said there should be no effect, but then Anderson localization says everything should get localized. So it's Anderson versus Anderson. And there were some early works trying to understand what the effect is. And then there was this very influential work, which we also discussed earlier in the morning by Christoph, of the quantum critical phenomena at the superconductor insulator transition using the Bose-Hubbard model with disorder, the work of Matthew Fisher and collaborators. So this was the state of the field when I began thinking about it. So we asked the following question, that a theory of the disorder-driven superconductor insulation transition must address the following questions. What is the nature of the superconducting state near the SIT? What is the nature of the normal state about TC there? Is the insulator gapped or gapless? Because the Anderson insulator is gapless, as you all know. Okay. And if there is a quantum critical point at which TC goes to 0, what is the other crossover line on the insulating side to make up the quantum critical regime? And finally, are fermionic degrees of freedom important at the SIT? Yes or no? So these were the set of questions we set to answer together with Nandini Trivedi. And all of the work that I'm going to talk about is actually work done with her. Okay, and she still remains a card-carrying member of the SIT community, unlike me, who seems to have fallen out of equilibrium with it. Okay, so she has ongoing collaborations with Abiyad over many, many years. Okay, so these are the papers that I will try to tell you about. And when I was making this list, I also found one thing, that people talk a lot about high impact journals. But I can assure you the most impactful paper we wrote is the one in PRB. It has the most interesting ideas, even though the least interesting colored pictures. It was all black. Okay. Very good. Oh, by the way, one last thing. Since I'm talking about old stuff, at least one slide or maybe two at the very end where I talk about open problems, because otherwise I feel students who are in the audience feel, okay, so you did everything, what are we supposed to do? There are lots of open problems, so I will end with Okay, so we chose to work with the absolutely simplest model where superconductivity and localization fight each other. So you have three terms: kinetic energy of electrons hopping on a square lattice, and at various places I will express all energies in units of t, so you can set it equal to 1. The second term is just the random potential, and the third term is an on-site attractive interaction. So if you just forget about the third term, setting u equals 0, that is the model that Anderson studied for Anderson localization. Okay? And in fact, in 2D, as was discussed this morning, you can Anderson localization for arbitrarily small values of V. So what is V? V of R is a uncorrelated, identically distributed random variable at each location R in the lattice. And it can be either attractive or repulsive and has this flat distribution. The details of the distribution don't matter so much. V sets the scale of disorder. Okay, so that's the Anderson transition. On the other hand, if you forget about V, you just set V equals 0, there's no random potential, then what you get is superconductivity, just singlet S wave. So this is the simplest model you can write down and try to solve however you want to solve it to study the fight between superconductivity and localization. So two remarks. First, even though Anderson localization, at least in this non-interactive regime, occurs for arbitrarily small disorder, the 2D SIT actually occurs at a finite value of the disorder. This occurs even if KFL is very, very large. This occurs when KFL is order 1. Okay. The second remark is that I am without interactions. Now, am I being smart or am I being foolish? Okay. Because whenever you write down a model, you have to ask, why did you choose to work with this? So, when we study superconductivity in BCS theory, we forget about the repulsive Coulomb interaction. The best it will do is to push certain things up to plasma energies and so on. Basic physics is not effective. When Anderson studied Anderson localization, he forgot about the Coulomb interaction. Now, why did those giants forget about it? Because with Coulomb interaction, the problem became very complicated. Okay. So as a theorist, it's a very good idea to ask, what is the simplest thing you can do? And how far you can explain the experiments. Now, maybe we will find when we compare with experiments in certain class of systems, this is a bad choice to make. But in other classes of systems, it's a reasonable thing to do. Anyway, it's the reasonable thing to do to begin with. And the reason why I'm talking to you 30 years after we started this program is because it turned out to be a very reasonable thing to do for a broad class of systems, not for all. Okay, so now how do you solve a problem like this? You certainly cannot do diagrams. And I will explain to you why actually even many of the approximations that you use within standard BCS framework just fail very badly at this transition. Okay, so I don't want to discuss these technical details because there seem to be very few theory students in the audience. But if anyone wants to discuss this in the Q&A, I'm very happy to discuss it. But what are the technical tools we threw at it? So we have thrown at it pairing of exact eigenstates, something that you heard about it. And here are the pros and cons of that method. We have thrown at it the Bogoliubov-Lejeune equations, okay? Thrown at it some self-consistent harmonic approximations to include phase fluctuations, and also done extensive quantum Monte Carlo. But I do want to talk about one point because this phrase keeps on appearing again and again in the literature and appeared even in some talks yesterday in this. Multifractality. Is this important for us or not important for us? Okay, so this is more about fundamental quantum Monte Carlo and analytic continuation. So this, anyone who wants to ask me questions with technical details on the methods we use and what are the underlying assumptions, how reliable they are, very happy to discuss that. But unless there is a pressing question, I want to move on to the physics rather than the methods. Actually, we also did some recent machine learning to do analytic continuation, which may be of interest to some of the younger people in the audience. Okay, so multifractality. So In this paper, amongst many other things, we also use the pairing of exact eigenstates in a random potential to generalize Anderson's approach to inhomogeneous systems, because Anderson had completely homogeneous systems. And it turns out, to a very large extent, you can actually reproduce all the Bouguereau-Baudrillard results that I'm about to get into in great detail. Okay, so in this approach, what happens is you need to solve a gap equation, which kind of looks familiar, except that the interaction term has the strength of the attraction, but some complicated matrix which involves the exact eigenstates in a random potential. And the structure is very important to solving the problem. But here comes the point that I'd also made earlier, that Anderson localization in 2D, non-interacting problem, the transition occurs at the blue point. Okay, the smallest disorder, and you become Anderson localized. But the superconductor-insulator transition, as I will show you, happens at a finite value of the disorder, or when KFL is of order 1. Now, where is multifractality known? It is known that in the vicinity of the Anderson transition, the exact eigenstates are multifractal. Okay, but this multifractality has nothing to do with the exact eigenstates that you must use when you mathematically study the transition here. So I know it sounds very fancy to say multifractality, but I would really ask the experimentalists to ask their theoretical colleagues who are pushing their term on this, what is the experimental evidence for multifractality? Okay, very good. So here's the first thing I'm going to show you, and here you'll see why BCS theory ideas just completely fail for you. Okay, so let's do a self-consistent. Yes, please.
Sorry, can we go back to this idea of multifractality?
Yes.
Because so in some of some papers you see multifractality involved in the SIT, or
what is the evidence for multifractality?
I mean, yeah, well, experimenting, I'm not sure.
Okay.
But okay, they claim, at least they claim that it's valid close to the SIT, so you don't agree.
It's absolutely, there is no evidence. Only multifractality is known for Anderson localization in 2 and 3 dimensions near the Anderson transition. Yeah. Okay, so let's do Bouguereau-Baudrillard mean field theory, self-consistency, which I think most students have an idea of what that is. So what you compute there is a order parameter or a pairing amplitude, which is CC or C dagger on site. And let's see what it does as you crank up the disorder at 0 temperature. Okay, and here is what you see. So first I'm just showing you a distribution of deltas as a function of delta, because this is the local pairing amplitude. So if you have weak disorder, then basically this distribution is highly peaked at the average value of delta, which means you can basically say it's spatially uniform pairing. This is absolutely central to Anderson's theorem and to Abrikosov-Goldbach theory, that the disorder has a uniform effect on the order parameter everywhere in space. So what is the numerics telling us? That as you increase the disorder, the distribution becomes broader and broader and broader, and in fact develops weight near 0. Okay, this is totally outside the purview of any diagrammatic approach or the standard Anderson theorem. So strong distribution, strong disorder, broad distribution.
These are numerical results, right?
That's the only way you can solve this problem. There is no way to get this result other than by either Bouguereau-Baudrillard or Poisson-Montefiore. Okay. Now the nice thing about the numerics is not only can you plot the distribution, you can actually ask what does it do in space. Okay. And what you find is that, look, as you are increasing the disorder, you find that the system sort of develops some granularity, that there are islands of superconductivity which have some non-zero pairing amplitude immersed in regions which have no superconductivity, which are white. Now, how did this happen? Is it something that it inherits from the disorder? And the answer is no. This is an emergent granularity. If you look at the random potential, it's quote unquote homogeneous because we took random and uncorrelated on an atomic scale. But when you solve the Bouguer-Bordesian equation self-consistently, the order parameter develops structures. It emerges. Okay? So it is not as if you had built in this granularity. And so here I clearly show you that there is a superconducting islands whose size is the dirty coherence level, if you wish, in an insulating sea where the order parameter vanishes. Now, of course, the question is, how do you see this experiment? Now, you could have said, oh, go and do scanning Josephson tunneling, but that's not an experiment that people can do very easily. It would actually, if you could do it, be sensitive to actually looking at the order parameter. So let's ask for more sensible answers. And certainly, nobody had thought about scanning Josephson tunneling 30 years ago when people were thinking about this problem. So what are the experiments? So first, I put in the slide on reminder and superfluid stiffness. Yes?
To the previous question, is there any physical intuition? Because if we say that okay, our order parameter is not correlated with distribution of disorder, why do we have this kind of, I don't know, symmetry broken phase in a sense?
So the thing is, it is correlated, but in a very subtle way that is very hard to see by eye. Okay, so let's get into what this means. Okay. But there is no, it's not that we made the system superconductive in some region. We just put a random potential. I told you what it was, you know. And this comes out of solving the Bouguer-Bordesian equation self-consistent. But just wait, I'm not done with this. I want to explain many things about it. So probably I don't need to talk about this because Christophe gave a fantastic and nuanced view of what the superfluid stiffness is. But let's go over it quickly. It's going to play a major role today. It's going to play a major role in my talk tomorrow for other reasons. So ds, the stiffness, is actually the free energy cost for phase fluctuation. So you have an order parameter, homogeneous or otherwise. If you twist the order parameter phase, how much energy does this cost you? Okay, this seems like a very theorist way of writing down some field theory or something. So experimentally, what do you see? It turns out the ds is exactly what you measure when you measure 1 over the London penetration depth squared. Okay, all this is in 3D. In 2D, we have a Pearl length, which is also related to ds. We discussed that in the thing. A third way to think about it is that if you were to measure the optical conductivity, then there is a delta function at the origin whose weight is precisely ds. And of course, this usually cannot be measured. You just measure in DC transport, you have infinite conductivity, but delta functions are not possible to measure. But what you can measure is the Kramer-Stronach, which is the imaginary part, and that also shows up ds. So this is another way to actually measure the superfluid stiffness. Now, why do we call it stiffness? And Christophe emphasizes very nicely. If you look at, say, Tinkham or some textbook, ds is written as h bar square ns over m star, and then ns is called the superfluid density. Okay, this is true if you have parabolic dispersion in the absence of disorder. But if you have disorder, if you have multi-band systems, there is no real decomposition into numerator and denominator. That Andrei Varlamov also emphasized this. What mass do you put in? What normalization do you put in? But this is a package deal, and this enters all physical observables. Okay. I want to make another remark. Ginzburg-Landau theory is wonderful, but Ginzburg-Landau theory can be very misleading on this point. Okay. It makes you believe that ds is proportional to or equal to, depending on normalization, the square of the order parameter. It's true in many situations, but it's also completely false in others. Okay? Forget disordered superconductors, about which maybe we don't know enough. Think about Kosterlitz-Thouless. There is no order parameter. There is a superfluid stiffness. Okay? So please be careful about this. It's okay, but it's dangerous in general. Okay, very good. So what we did in our numerics was to calculate the energy gap and the superfluid stiffness. The energy gap could in principle be studied using tunneling, and the superfluid stiffness could be measured using whatever techniques you have. And what you find is a very strange result, which perplexed us when we first saw it, that as you crank up the disorder, the superfluid stiffness crashes on you. Okay? But the energy gap shows some weird monotonic behavior, but remains finite. Okay? It turned out that in the Bogoliubov-Desjardins theory, you could never actually take ds to precisely 0, because Bogoliubov-Desjardins theory, being a field theory, doesn't have quantum fluctuations of the phase built into it. But we could build them in using either self-consistent harmonic approximations or quantum Monte Carlo, and ds actually goes to 0, and you get a superconductor to insulator transition. Okay? But the gap remains finite. So this is the quantum Monte Carlo on the superfluid stiffness is measured. Okay, so now we have to understand all of this. So let's try and understand this. So I will explain this a little bit later. Why does the gap remain finite? Okay. But first, let me focus on why the stiffness going to 0 controls the phase transition. So actually, one can look at the reduction of the superfluid stiffness due to disorder in many ways. Optical sum rule is one way, but I prefer this because it's completely hand-wavy, but also completely correct. Okay, so I gave you the intuitive picture that it's the energy cost for a phase twist. So if I have a homogeneous order parameter, then if I apply a phase twist to the boundary, that phase twist is accommodated uniformly in my system. So I get a certain superfluid stiffness. However, if I have an inhomogeneous system where some places the order parameter is becoming very small, if I twist the boundary, you'll hide all the phase twist where you're paying the least cost for it. So as a result, you pay a lot less energy cost and the superfluid stiffness dies on you. And of course, if your islands become disconnected, as it were, superfluid stiffness goes to 0. Okay. And if this sounds like hand waving, this can be made into a rigorous variational bound in this old paper of ours. Okay, so what is driving? What is the physical picture? It's quantum fluctuations of the phase on top of this inhomogeneous. Yes, please.
I have a question on the picture of the phase twist. If the phase twists more in the regions with low phase stiffness, does this mean that the supercurrent that maybe flows is only flowing in the region or preferably flowing?
No, if you want to think in terms of critical current, it's like the critical current is determined where the superconductivity is the weakest. That's a mental picture you can have.
Yeah, thank you.
Yeah, that's where it will break down. Okay, so let's get a more physical picture before going into other things. So it's the quantum fluctuations of the phase on top of a very inhomogeneous local pairing landscape. So the physical picture is the emergent granularity leads to an effective random quantum XY. And that loss of stiffness basically randomizes the phase on the superconducting islands when you lose superconductivity. Okay, so there is this paper that we wrote with Mason Swanson and Yen-Li Lo and Nandini, which I will not discuss. I know that some people in Christoph's group are trying to think very carefully about it, simply because I didn't want to get into random quantum XY models and so on. Okay, so here is the first picture. I still have to explain to you why the gap remains finite and so on. That if you look at regular superconductors, non-disordered, they are in this plane, and at the transition, the energy gap collapses and the superfluid stiffness collapses. But what I've told you is that along the disorder axis, the energy gap seems to remain finite, but it's the superfluid stiffness collapsing which is giving rise to the critical point. Yes, Alki. So now, why does the energy gap remain finite? What does it mean? So let's try and correlate the local energy gap, which is what you would measure in SPM measurements, with the pairing amplitude, which is hard to measure experimentally, but in our numerics, you can do it. So here in the top picture, I have the local pairing amplitude. In the bottom picture, the local energy gap. The reason why, again, words are very important here is, in BCS theory, the pairing amplitude and energy gap are one and the same thing. They call the gap function, the gap, something, the something. Here they mean very different things. Okay. So also look at it. Here the way we've colored it, dark means the large pairing amplitude, whereas here the way we've colored it, dark means a small energy gap. Actually, black would mean zero energy gap. So everywhere there is an energy gap, but darker means, so they seem like they're completely anti-correlated. In regions where you have a high local pairing amplitude, we have a relatively small energy gap, which is also not something you would have guessed. So why is that? This puzzled us. But then, because you do this kind of numerics, you can interrogate the numerics and you understand exactly why this is happening. So what happens is that if you look at the spectrum, local density of states in this large pairing amplitude region, you see a BCS-like gap with coherence peaks, and that's the small gap that I'm talking about here. Okay? But if you look at the distances at these white regions where there is no pairing amplitude, you still have a gap, but it doesn't at all look like BCS theory. There's some other random stuff going on. Okay, so this is the superconducting blob. Now, why do I call this a hill and I call this a valley? So let's understand that. Sorry, perhaps I'm mixing metaphors of islands, oceans, hills, valleys, but forget about that metaphor. Just fix on this. What you can see here is that this is a region of very high average random potential, which is why it's a hill. There are no electrons that you can take out in tunneling, but you can, if you're willing to pay a cost and energy, put electrons there. Whereas this is a valley, so there are already lots of electrons that you can take out in tunneling, but there isn't much place to put an electron in there. Okay, so this anti-correlation between them, we can get an intuitive understanding in terms of the pairing of exact eigenstates. Perhaps in view of the time, we can postpone this unless people want this intuitive understanding right now. Or... Okay.
Yeah, we want that.
You want that?
Very much more.
You want that. Okay. So in the pairing of exact eigenstates, I start with an Anderson insulator. Anderson insulator is gapless. Right? That's very important. Gaps are a mobility gap, but spectrally it's gapless. Featureless density of states. Now, if you look at the attraction, it actually affects electrons only near the chemical potential. For electrons near the chemical potential, it opens up a superconducting gap. That's the small gap. These hills and valleys correspond to localized states which are far from the chemical potential. So from the perspective of the chemical potential, they were already gapped, as it were, in the Anderson insulator. They were already far from the chemical potential. That's the physical picture that emerges from this.
Excuse me.
Yeah.
So the calculation of density of states has been done just taking the dispersion of the energy from the Bourgo, solving the determinant of the Bourgo jet equation.
That's right. That's just looked at the energies of this inhomogeneous Bogomolov region. The other way we do it is when we run quantum Monte Carlo, which is what I'm showing you here. Then, of course, you can compute the Green's function. And then you actually compute gaps. Either you look at the fall off in imaginary time, or you do some analytic continuation. And here, I think I'm showing you data from analytic continuation. So we've done it using multiple ways. Yes. Okay. So now let's look at the evolution of the spatially average density of states. So what you find is, oops, sorry, that's not what I want. If I look at the system at very low temperatures, because it's quantum Monte Carlo, we are not at zero temperature, somewhere there. As you increase disorder, you find that in the superconducting state, you see these coherence peaks. Okay? But as you increase disorder, the coherence peaks disappear, but the gap remains and in fact grows exactly as our Bogomolov region calculation and pairing of exact eigenstates states. So the gap in the density of states persists across the SID, and the coherence peaks are there only in the superconducting state. Okay, so now I have told you from the superconducting density. I can use the BKT formula and compute TC, and TC goes to 0 here. And this is the energy gap as computed from here, in this case, quantum Monte Carlo. But actually, this dashed line is just a guide for the eye. But the fact that the gap seems to be increasing is again something that we predicted long ago based on a different calculation using pairing of exact eigenstates. And actually, Aviad is working on this problem, right? So anyway, the bottom line is that the way in which this is happening is you get phase incoherent superconducting blobs in the insulator. Because of that, Tc has gone to 0, but there is pairing in this insulator and the energy gap remains. Okay? Since the fermions remain gapped at the SIT or the quantum critical point, there's, if you wish, you can write down a field theory which is purely bosonic to describe it. Okay, then you can ask, what is the evolution of the density of states through the finite temperature transition near the SIT? So I'm in not weak disorder, I'm strong disorder, but on the superconducting side. And again, this is what you see, that the gap in the density of states persists as a pseudo gap well above Tc. But the coherence peaks basically lose their weight as you go above Tc and eventually are gone. So what do I, the word pseudo gap is highly used, abused, overused. So what do I mean by that? I mean a suppression of low energy spectral weight, which you can see in the density of states. However, here we know where it arises from because the model is simple enough that it has only one source, unlike in many other situations. It just arises from preformed pair fluctuations because even the scale of this pseudo gap is the same as the superconducting gap. This is by no means saying that in many other situations like the cuprates and so on, where the pseudo gap is seen, this is the origin. I do not mean to make any such assertions. So here you can see from our quantum Monte Carlo pseudo gap, this is I'm in the superconducting state. I see very nice coherence peak, a deep gap. I go just about Tc, the gap remains. I go higher, still a little bit of suppression. Eventually it goes up. Okay, so we also did some resistivity calculations. These are quite tricky to do. And anyway, at least at the level at which we could talk about this, when we run the sector, this is the direct insulator function is the same. So let's take stock. Is that a question? Yes.
So, with respect to this anti-correlation,
yes.
So you said the argument is that there are some regions that you have islands of density of states in Fermi energy, islands above Fermi energy, and the density of states is localized. I didn't understand the next step in your logics. Or why does this mean that you're not going to have a superconducting gap? The drawing looks like there's a superconducting gap, although the density of states moves from one side to the other. So what is the logic there?
So the thing is, suppose I have a flat density of states. Yeah. So this is I'm doing a very approximate calculation, pairing of exact eigenstates, unlike the more exact calculations to get insight into the problem. Okay. So I have a flat or featureless density of states of the Anderson insulator. Now I turn on attraction. What happens is that if I turn on a weak attraction, it's only a narrow range of energies near the chemical potential where a superconducting gap opens up. In weak attraction doesn't impact things far from the chemical. Fair enough. I mean, that's what happens in BCS theory. So if there are regions which are far from the chemical potential, which are not impacted by, they already, as with respect to the chemical potential, they're already at high energy. And that's where the pairing amplitude was 0.
But where does localization come in?
Because this pairing of exact eigenstates, I'm not using plane waves. I'm using the highly disordered states near the SIT as input into this calculation. So they know all about Anderson localization.
And this means that like an electron cannot pair because there's not enough, he can't find its pi partner, or what is the...
Okay, I don't want to say, so there's so much I trust in the pairing of exact eigenstates So I don't want to put in more. I mean, we can do better calculations. We see something, we do a more approximate calculation, we can gain some insight into it. I don't know whether I want to push it any further. Yes, Anu.
Yeah, you have this disorder which is completely uncorrelated. So there is some probability to find an extended region of high potentials, and then you have a state.
So I have some hidden slides on quantum Griffith singularities, which is where you're going.
Okay.
I didn't want to go there, and I probably don't want to go there, but I'm happy to go there later.
Okay.
Yeah, because that comes from rare regions. That's the question you're asking.
And so it may not directly give you the length scales for your island.
Yes.
That's probably a more difficult
Yes.
length scale.
Yes.
In the model, is the particle density uniform everywhere?
No. No, it's not. Because with a random potential in the Anderson localization problem also, the particle density is not uniform.
And here, I mean, does the typical variation, Fourier space, of the size of distribution of particle density that correlates with the spatial?
No, actually, if you look at this PRB paper, you'll see that the density correlation falls off very rapidly, whereas the pairing correlations have this coherence length scale. So we discussed that there. I can show you that figure. I don't have it handy, yeah, but it's there in our paper. Yes, please.
I'll just make a comment on behalf of Nandini.
Yes.
And that is the fact that you have these states very far from the mechanical potential is the reason. I mean, this is the explanation of where the states go away from the coherence peaks, because you need spectral weight
Yes.
to maintain spectral weight. So the fact that you have them there,
yes,
explains why you don't see them in the experiments close to the gap.
She's certainly been thinking about this much more recently with you than I have. So please, please add that. Yes, please.
It's very much like that you start from an Anderson insulator AU. So the normal state of your superconductor is an Anderson insulator.
No. Because near the transition, the superfluid density is very low. So fluctuations of the superconductivity permeate into very high temperatures.
Certainly, but this is coming from the fact that you introduce superconductivity in a system in which the normal state would be Anderson.
I mean, if you go to very high temperatures where you can ignore the effects of the attraction, the answer is yes. We are just trying to.
There is any evidence that the normal state is Anderson.
The normal state that people measure is full of superconducting fluctuations over very wide ranges. So you're asking for what happens even above.
Yeah.
Well, gaps close, I assume. I don't know whether there's any evidence there. But we are studying the fighting of Anderson localization and super. That was my starting point. So it's not as if.
It's more than that. More than that. It's the fact that the Anderson is in some sense the normal state of the
It's not just about DC. For a very broad range of temperatures, it's not, because near the SIT, the superfluid density is very strong, and therefore, and on the insulating side, also it's not, because it's a gapped insulator. Anderson insulator is not a gapped insulator.
But I have to say that to very high disorder, you go deep into the insulator, you see deep to the heart. So it's
okay. Fine. It is what it is. Okay. So anyway, I have. In fact, I'm saying that the inhomogeneous insulator with local pairing and the energy gap both make it completely distinct from the Anderson insulator. So the answer is right here. And also the transition is at a finite disorder distinct from Anderson. So it's really quite different from Anderson localization. But now this raises the question, who is coming down here? Like, if this is a quantum-critical point, I have shown you everything else, but what is this scale? Okay. This is another question we sought to answer. So we looked at the energy gap for pairs, and to do that, we calculated the imaginary part of the pair susceptibility. And what we found was that in an insulator, there is a pairing gap, meaning it takes a finite amount of energy to add a pair in an insulator. Not surprising, it takes a finite amount of energy to even add a single particle in an insulator. And in the superconductor, it takes no energy to add a pair because you can just slip it to the condensate. But now let's ask, how does this E pair, the spectral gap in the imaginary part of the pair susceptibility, scale with disorder? And this is what you find. Okay, so the pairing gap is not 2 times the single particle energy gap because of the attractive interaction in the insulator. And in fact, the pairing gap is the crossover scale that goes soft as you approach the SIT from the insulating side. Okay. So again, we have to be very careful. This is TC or rho S. This is the gap for pairs, and that's the gap for single electrons.
So the gap for single electrons is what you would measure in SDM, for instance, and the gap for pairs is not really accessible, but it's the energy that you would need to put an additional pair inside, right?
So this is true. I don't have a very good answer for an experiment that would measure this. I think one should think about transport. I think that was one of the open questions that Christoph had put up. Transport in the insulator, because it costs much less energy to make a pair than a single electron. So transport, maybe some hopping of pairs and so on. This is pure speculation. I have not calculated anything. Yes, please.
That we made such a plot. On the right-hand side is the activation energy for the activated resistance of it. I don't know.
In that case, it's not necessarily pairs that tunnel through. It could be electrons hopping between superconductors.
My feeling is pairs.
I mean, I think one has to prove that. I mean, for instance, these I think he showed some data of Jim Wallace and others of, putting holes, and that there are pairs in the insulator.
Yeah, sure.
Yeah. Okay, now the question you can ask is, this is some simple model, the simplest model you wrote down. Can it really describe reality, right? And I would immediately like to say it's not as if it can explain every superconductor-insulator transition seen in the world, okay? There are all kinds of superconductor-insulator transitions. Some of them have anomalous metals, other ones don't. People discuss filtering and not filtering, which is totally beyond my ability to understand. Okay, but there are many materials for which this model has provided very good evidence, because much of this evidence came 10 years after the calculations. Okay, so here are predictions of the inhomogeneous pairing. Here are predictions of the change in the nature of the spectrum. Here are predictions of the pseudo gap, and many of these things have now been seen on materials like titanium nitride, niobium nitride, indium oxide. The people in the room know much more about the experiments than I do. The STM experiments of Benjamin Sassapé I show here. Okay? They look very, very similar to what we predicted, showing single particle energy gaps as measured by STM and how they are seeing a very homogeneous state of superconductivity. These are the tunneling spectra with and without coherence peaks. There are also superfluid stiffness experiments, and there are many other experiments by Aviad and Pratap Raichaudhuri, who will be here, Batujina Wallace, and many others trying to get this. Some very recent experiments. So here is an experiment that Nandini asked me to show you. And I don't know too much about this paper, to be honest, but you can look it up. It just appeared in TRL. That there is spectroscopic evidence for a disordered induced quantum phase transition in monolayer iron selenide, tell you, right? Superconductors, where they see hard gaps with some coherence-like peaks in the superconducting state, but they also see large hard gaps with no coherence peak in what they think is a paired insulator. Again, this is an STM experiment from China. And she gave me some slides here, but I don't know what the latest is, but they are right here. So you should go and see this poster from Alia's group. They see evidence for an increasing gap beyond the SIT into the paired insulator. So I will say no more there. And so that's my summary. We answered the question that there's a highly inhomogeneous pairing amplitude, highly inhomogeneous local energy gap. The transition is driven by phase fluctuations, this low superfluid density. The energy gap survives about TC on the superconducting side, that's the pairing pseudo gap. The energy gap actually survives into the insulating state. So it's a gapped insulator with single particle energy gap. And there is the gap of pairs on the insulating side, which actually goes soft at the transition. And so if you want to write down a field theory for what's happening here, it's a bosonic field theory because the fermions are all gapped out. So that's my summary, and I will end that. And Anu, I think I will not say much about the hidden slides I have on quantum Griffith singularity, except to say the following, okay? That the quantum Griffith singularity in this model do not impact the single particle spectral function. The single particle spectral function remains gap across the phase transition. They do impact the pair spectral function. Okay, we see evidence for that, and that is completely consistent with statements that have been known from dirty bosons for what you would expect in that situation. So let me just keep it at that. I'm happy to show that to you in private. Okay, so that's end of part one, and we can take a break, we can ask questions. I have a part two if people are too tired, we don't have to.
So when you open a gap for pairing, but people still see the pairs from the little proxy effect on the insulating side.
Yes.
What does it? How can we
not calculated that because the transport should be hopping transport of pairs, and I'm not exactly sure how that would play out when you want to, because is there phase coherence when you have hopping transport? I'm not ready to answer that question. Perhaps people here have thought more about that problem than I have. It's not obvious to me. Right? Usual little bath experiment we understand. There's a condensate. Please.
So could you please comment maybe on the sort of amplitude versus the phase?
Yes.
So in your model, you destroy both
yes.
amplitude and you destroy the stiffness.
Yes.
So, but what to do to sort of make a preference between the, well, how to change the model, what to do? And do you know of experiments that?
So the thing is the inhomogeneity of the pairing amplitude per se. It's hard to detect experimentally unless you were to do scanning Josephs, which I think is right now a fairy tale, to be honest. But the energy gap in some cases, but it's a very tricky experiment. Actually, we can discuss that. It picks up a flake of visco, then brings it back, and it's visco to visco tunneling. I don't know what you would do here. Okay, anyway, yes. I mean, I guess if Seamus Davis wanted to put in enough effort into this, perhaps it would be done. But it would be like a very heroic experiment. It's not some ordinary simple experiment. So, but the fact that that's the only way I know of that anybody predicted 10 years before the experiment that the energy gap measured in tunneling would be also inhomogeneous is definitely seen by multiple groups, like Sasape, Pratap, so on, doing STM. Simultaneously, they see in their kinetic inductance, superfluid density measurements that's driving the phase transition. I don't know. It's a package deal here. I don't know what you would do. I don't know what Coulomb interactions will do. That's a very difficult question. You know, as we know, forget superconductivity. The disorder plus Coulomb is an unsolved problem. Crouch-in. So if you throw in that into the mix.
But you have immersion granularity, right?
That's true.
And then, so you have islands.
Yes. Of pairing amplitude, but not density fluctuations.
You mean that the carrier density, the electron density?
Yes,
is
the
already-
So that was the question that was asked, whether the electron density in this model itself becomes inhomogeneous on the scale of the superconducting ions that emerge. And the answer is no.
Not maybe on the scale of the superconducting ions, but also elsewhere. I mean,
So it is definitely inhomogeneous as it is in the Anderson institute. Now, once you put in Coulomb interactions, that would also have an impact. That particular story, right?
Yeah.
Yes.
Charge,
Right?
charging.
I'm well aware of that. Yes. Okay.
I wanted to ask why do we need to kind of look for a exotic energy scale when you see that goes down zero together with the OS? And we heard from Andrea yesterday that TC was the most natural energy for this problem.
So I'm not looking for an exotic energy.
Because TC, we know we can measure it goes down to zero exactly at the transition, and then this, why do we need an extra?
Which extra scale?
You're
I didn't need another one. It's just that I was saying if you have a quantum critical fan on one side, I have a quantum critical fan, I have one scale, but now I have a quantum critical regime. So what's the crossover scale? So I need that to define a quantum critical fan.
Experimentally, usually people put T0, like over there in Chapel, like Crystal.
What about the other side?
No, I'm talking about T0, the exponential.
That's a separate story. I'm not putting it. Yes, please.
Does it make sense to ask how many Cooper pairs are in such a?
But they're varying size now.
Huh?
The size itself
There
varies.
is a size, and there should be a number of.
I think even for BCS superconductors, this idea of how many Cooper pairs is a pretty ill-defined. You said that yourself, right? Because, okay, like I think this is most effectively stated in helium-4. How many atoms in the condensate of helium-4? Answer is no, it's 10% because of the strong repulsive interaction. Then you ask, what is the superfluid density, which you can ask, it's a parabolic system, of helium-4 at zero temperature? Answer, 100% of the helium atoms because of Galilean invariance and measurements too. So this number of Cooper or number of particles in the condensate and superfluid density, we have to be very careful. I think the best thing to do is to ask, what experimental observable are we asking for? Can we calculate that?
So the background of my question was whether, say, one can say that the island is in a way superconducting, that there is enough bearing and interaction to sustain that, because eventually it's a mean field thing, right? You don't have a single Cooper pair. Typically, you need some mean field around it to have it paired. And my difficulty with preform pairs is that I don't see why they pair if they are alone.
They are not alone. Which now are we asking about preform pairs about TC on the superconducting side, or are you asking about the insulating? So where people don't on the insulating, people don't use the word preformed. I mean, actually, I don't know. Whatever. Okay. So you're saying you're absolutely right. If you go far enough into the insulator, where the islands become tiny, eventually you will lose everything.
Yeah.
You have to. Yeah. Right? I mean, people understand that from old work on nanoparticles and what size, so you will lose everything. I'm actually discussing what's happening in the vicinity of.
So there are no isolated pairs.
Of course not. No. So then it's.
So this means that this diagram here, if you go far away at very high disorder, the red curve goes back to zero.
This is not the right model.
Okay.
It has to.
I think it has to. It goes to fermionic.
Yeah, of course. Everything will dark. And if you go far here, we've known what happens for, I don't know, 70 years. body incoherent reefer. So, okay, so we want to study that which we don't understand and which is not boring.
So perhaps a bit related.
Yes.
As far as I understand, to have the superconducting islands,
Yes.
so that's the coherence length that sets the size.
I mean, I'm just defining it to be the coherence length now.
Okay, but to have it in these numerically finite systems,
yes.
As far as I remember your papers, your interaction U, the attractive, is quite high.
Yes. So this
But
is
in the beginning, you yourself made a comment that when U is high, there might be BC.
Yes.
Instead of
So no, these are very good questions, and actually the second part of my talk will try to answer these questions. Yes, it's a very good question. If U is very tiny, okay, all length scales like coherence lengths and so on are huge, and all numerical methods fail. Okay, so what is the best one can hope to in all of these numerical methods? It's to at least start with situations where the original superfluid density is much higher than the single particle energy gap, because that is something which is not at all what happens in DC regimes. We have numerics. That's one thing. The second thing is that this pairing of exact eigenstates, which I didn't really dwell on very much, is the most approximate of all the calculations we can do. That calculation can actually be done for very small U. Why is that? Because the hard calculation you need to do is to do Anderson localization on large systems, which you can do. It's a non-interactive problem. Then put it into there. And everything we see here is reproduced by that approximate calculation. That's the best I can say.
So is because U is big, the normal state is not the Anderson insulator.
No, actually, even if you,
because when you go to people, then so
okay, I don't know what to say, but experiments definitely see that near the superconductor-insulator transition, if I raise the temperature, I see large regions of pairing pseudo-gap. That's not an Anderson insulator normal state. Experiment will definitely see paired insulators. That's not an Anderson insulator. That's what we find.
So we're talking about experiment. I totally agree with
That's
that.
what we find in the theory too, and we predicted it before the experiment. That's all I'm saying. Andy?
Yeah, sorry. There was a point also about the multifractality of the wave functions. My question is it in fact that we study here the 2D system, or will something change with systems with mobility edge on the Anderson transition point?
Okay, I have done nothing on the 3D problem. So I don't want to say anything about something that I have not computed. Now you can ask me, why did I do nothing on the 3D? Right? And the answer to that is, everybody who has done this has seen costless Howless transitions at DC. So the experiments are on 2D systems. So I'm happy sticking to 2 dimensions.
Continue with the multifractality. So you were working with these exact pair eigenstates. So those for very small U, or
no, that eigenstates are for 0 U, which is why you can do huge systems.
How does the presumably it's quite multifractal for small disorder already, because that's where the Anderson
that's right.
Critical. You crank up disorder till you get more localized.
Yeah.
But you're working with finite systems, so
you are obviously working one. Maybe you can do.
So it may be multifractal on the scale.
I think it's just a buzzword that people love to use.
It looks multifractal.
There's nothing multifractal about it. I mean, to check that there's anything multifractal about it, you would have to look at higher moments and see that they scale in some very interesting way.
So just to complete where I'm coming from, I've worked a lot on quasi-periodic systems. So the disorder, quasi-periodic, right? So the disorder, it's very inhomogeneous, but it's not random.
Yes.
And what I find is, what we found is, there are gaps and there are local pairings, and they are not correlated.
They're anti-correlated.
No, they're not anti-correlated. Just the wave functions are multifractal.
There it's a different story.
Exactly. So it's very different. That's why I'm curious what yours.
So there I agree. The wave functions are multifractal.
Yeah, here they're exponentially localized, presumably where your SIT is occurring. But have you checked that?
Yes.
Yeah. Compared to your length scale,
yes,
more localized version. Yeah, so they're not.
I have another question about fractal. So it's not to trigger a violent debate or anything. It's just that I don't understand. So there are all these papers by Pagan and all this school who advocate that there is multifractality. And so I don't understand the view.
But have you asked them why they advocate?
Well, okay, so let me say what I have understood, or from a very naive experimental point of view. Okay, multifractality for me is like you have a different, it's so the wave function can reappear everywhere. So you basically end up with a very disordered and inhomogeneous system, and don't yell at me. Looks to me very similar to emerging granularity, and I would like to understand how it's different.
It's exactly what Anu said, that multifractality. Okay, so first of all, let's ask what you expect a generic critical phenomenon. Forget disorder. You get power law decays.
Yes.
Right? Power law decays. Okay, and those are described by single exponents, as it were.
Yes.
Multifractality is a way people have understood very interesting things about Anderson transitions and the nature of the wave functions at Anderson transitions by looking at moments of these and saying that they are, it's not that the second moment, the fourth moment, and so on have power law exponents which are trivially related to each other. They are related in some non-trivial way. Okay, so it's some self-similar structure, not just a single exponent. Here, things are exponentially localized. It's not a phrase you can just use to say it's very disordered something. It has a power law structure with a rather delicate multifractal structure, right? It has a mathematical meaning. Here, the wave functions are exponentially localized. So you should ask those who talk. I don't want to talk more about multifractality.
Okay.
Yeah. You should ask them who pushed for it.
There will be some of them in the second.
Fine. Happy to interact with them.
Maybe another question. So more recently, people looked at Dirac dispersions in presence of disorder, and there was this works by Philoche and May Boroda, where they figure out the localization potential for the Dirac electrons, which is then quite different than the actual V potential. Your story, the valleys and the hills of the V potential sort of push the electron onto the island, so they end up with a gap. But then for this Dirac, it would be somehow quite different.
Actually, I was just told this morning, I'm totally unaware of this literature. I would love to find out about it. That actually, for weak disorder, in fact, if you have a Dirac dispersion, the beta function is a different sign from Yang of 4. I didn't even know that. I just learned that this morning. So sorry.
Yeah.
But please give me those references. Yes.
I have a much simpler question. I'm very impressed by these results and how well they describe some materials. Can you make a comment on, like, if I have a material, can I have a clue whether it would be described by that or not? Some borders to this that we can easily see, or do we have to guess beforehand?
This is an excellent question. Because if somebody said, will molygermanium be described by this? Or is niobium, nitride be described? I don't think I can say that. Maybe the experimentalists have some insight which I would be happy to learn. So I have taken the attitude that let's make the simplest model and let's see how far it goes. If it fails, it fails. If it works, then it works. If there are aspects in which it fails, then you have to add something to the model.
I think this is.
So I don't know. It's an excellent question. I don't know the answer.
I think this is a very good idea. But you said, for example, there's no Cooper interaction, Coulomb interaction.
Coulomb interaction.
Yeah. Does this give a clue? I don't know.
The problem becomes insoluble in any simple.
Oh no, I don't want to say that you should do this. I mean, maybe there's some range of materials where people know, oh, Coulomb interaction is super duper important.
Actually, I would love to hear from the experimental experts whether they have some idea when Coulomb interactions are really important in this set of problems. I don't have anything useful to say.
I think some things can be done by kind of trying to screen out Coulomb interactions and looking at the stuff. That would be the first thing to do. We've done a bit of that, but I think that is definitely one way.
Okay.
I think in the insulating phase it should be.
For instance, in a very different world, when people say the Hubbard model describes smart insulators and anti-thermal with the long-range part of the Coulomb. Now, you can ask, are there properties for which it's very important? The answer is definitely yes. But for other properties, the answer is apparently no. So, I don't know what to say about this.
Thank you very much, gentlemen.
Thank you. Okay, so if people are not already tired of me, I want to turn gears and talk about a much simpler model. Okay, so I wanted to ask, suppose I come from the insulating side and ask, how does superconducting instability develop here? Now, the only way we know about superconducting instability is a Fermi surface, right? But the insulator had no Fermi surface. So what happened? So we asked ourselves, is there some simple model again, whether experimentally relevant or not, in which we can answer this question? What do you mean that the insulator becomes unstable to bearing? And actually, this model is very simple. It has no disorder, but it also gives insight to the kinds of questions you were asking me, that your U was very large and maybe that was a problem. Because in this model, we can do diagrams, we can do quantum Monte Carlo, we can throw every trick in the book. So that gives us some more confidence in our numerics also. Okay? Okay, very good. So actually, since I'm in France, I should say that this work was really inspired by this probably not very well-known paper of Philippe Rozier's. And I would also like to acknowledge that at a very early stage in my career, I got a lot of encouragement from Philippe, even though he was not my doctoral or postdoctoral advisor when I was a young man, so for which I'm very grateful to him. Okay, so let's try to ask this question. So our goal is the following. Let's introduce a simple fermionic model, which is translationally invariant, no disorder. But I will make it a band. And then I will ask, can superconductivity develop in it? And if so, how? Now, of course, you could have a boring answer. You dope a band insulator, then a small Fermi surface develops. That's not, then there's a Fermi surface instability. That's not the question I want to ask. I want to ask, can superconductivity develop in a system without a Fermi surface? Okay, so I think what we did was to really take a very specific model so we could calculate using a variety of tools. But I think the general story is true for any band insulated to superconductor transitions, although there aren't too many experimental examples known. Okay, so here's what happens. I'm giving you the summaries, and then we can rush through the details. That at the two ends, we have a Fermi insulator, that's a band insulator we know and love, and we have a BCS superconductor. But actually, the way in which you go from a band insulator to a superconductor is through, first there is a bosonic crossover on the Fermi side, and there's a bosonic crossover on the superconducting side. So what do I mean by that? I'll show you that in a Fermi insulator, the lowest energy excitation is a charge E fermion. But then there's a crossover that the lowest excitation energy becomes a charged 2e boson, precisely of the kind you saw in the SIT. And that goes soft. And when the charged 2e boson goes soft, you go into a BEC regime. And in the BEC regime, then you cross over to a BCS regime. I have to, of course, tell you what this parameter is. It's going to come. And we'll see this here. We distinguish the Fermi to Bose crossover using which is the lowest energy excitation. And here we distinguish between the Bose to Fermi crossover, if you wish, by looking at the topology of the minimum gap locus and the gap at singularity. I'll explain both those. These are all measurable things in principle if you could realize this one. Okay, so we want a translationally invariant system with no disorder. So you need at least 2 orbitals or sites per unit cell, otherwise you won't get true bands. Yes?
No disorder, when you talk about a Fermi insulator, you mean a band
insulator? It's a boring band insulator, the most boring band insulator.
There's nothing to do with what we know about ESA.
No. I know. I told you. I want to have a simple picture where everything I showed you appears, but no disorder. And we understand how this is a theoretical game. You can go to sleep if you want, or you can tell me how you can realize in the lab. I'd be eternally grateful.
Tell me
one or the other.
Tell me what the parameter is.
I'll tell you. I'll tell you. So we take attractive interactions. We take a non-bipartite lattice because we want to suppress charge density order. So we could have taken a square lattice with 2 unit cells per, or 2 orbitals per unit cell, but that gives you CDW. So for concreteness, we just took this simple model of a triangular lattice. Triangular lattice frustrates charge density waves of the kind that would trouble us. And we coupled 2 copies of it. So there's a hopping T in the plane of the triangles and a hopping T per. That's just a model, because now you can see that I have 2 layers coupled, so I'll get 2 bands. That's all it bands. Okay, so that's my model. Okay, I have hopping in the layers. I have hopping across layers. I have an attractive interaction and a chemical potential. I set the chemical potential so I'm always at half filling. So because I don't want to create a Fermi surface. So I get a band insulator in the non-interacting limit. And I'll tune the band structure to obtain this SIT. So let's see how that works. Okay, so I adapted this picture from my dear friend Asa Auerbach's book. So this is Asa. And he's saying, okay, what tools should I throw at this problem? This is diagrams, quantum Monte Carlo, and there's a large bear of maximum entropy hiding in this. Okay. So here's what we do. We can change the band structure by T over T perp, and we can change the attraction. And now we can really do very small u, and here we do diagrams and theory. We can do very small t, and that's an atomic limit which we can solve. We can solve very large u, which is a strong coupling bosonic limit, and we can do quantum Monte Carlo. So we can just throw every trick available to us to solve this problem. Okay, so if I start in the non-interacting model at half filling, clearly I see the following. I have 2 bands, and if the hopping in the plane is small compared to the interplane hopping, which is very large, these 2 bands are just widely separated, and I get a band density. Okay, this is the triangular lattice density of states. But then you can prove very trivially that if you crank up the hopping in the plane, eventually these 2 bands come together, and I get a metal if I have no interactions whatsoever. Now I can ask, what happens at weak coupling? So at weak coupling, I can turn on U. And what happens here is that I have no Fermi surface at this point, but I'll show you that this band insulator persists at very tiny U's, but it immediately becomes a superconductor for any small value of U as soon as you are to the side of 2 nines. Okay. So now I can do diagrams. I just look at the pair susceptibility, and I can ask, where does the pair susceptibility diverge? There's my SIT. Okay. Then I can ask, so that's the transition from insulator to superconductor. And then I can look at the gap to pair excitations in the insulator by looking at the pole in the pair susceptibility. I see the pairing energy becomes soft, exactly as I had in my other problems. Okay, this is from diagrammatic perturbation and sum to all orders, of course. And then I can ask, what about the single particle energy gap? The single particle energy gap in this problem is changing as I change the band structure, but is finite at the SI. So it has all the features that I showed you in a much more complicated numerically done problem. Okay. Now done completely analytically. And there are three unusual features. The one particle energy gap remains finite in the band insulated superconductor transition. The two particle energy gap is actually much smaller than the one particle energy gap, let alone twice the one particle energy gap, and becomes soft at the transition. Okay, and then we can use standard BCS theory on the other side, solving gap equations and number equations analytically. And what you find is what I show you here. Okay, that the energy gap is finite, but then has this weird shape, which I'll explain to you. Delta is the pairing amplitude. Okay, and this is the superfluid density that you calculate from here. So let's go over this in a little bit of detail. So the energy gap, single particle energy gap, was just the band gap in the band insulator. Then suddenly it kicks up. Okay, so it's a band gap in the band insulator, and why does it kick up? Well, we'll come to that in a second. But the energy gap deep into the superconductor is in delta, which is what you expect for any BCS superconductor. But in the middle, you have a BCS regime where the two gaps add in quadrature. So you see this weird kink in the energy gap, which you see even in the numerics. So that I want to show you something so that you have faith in my numerics also. Okay, so here also phase fluctuations dominate over the breaking of pairs at the gap scale. So this is also a phase fluctuation driven. Here there's no inhomogeneity or nothing. But at the SIT, it's the superfluid density which is driving the phase transition. Okay. Now, how to identify the BCS to BEC crossover on the superconducting side? And there are two ways to do it. One thing you can ask is, what does the Bogoliubov excitation spectrum look like? And where is it minimum, which is I call the minimum gap locus. And as you all know from this textbook result, the minimum gap locus is at epsilon k equals mu. So that's on the Fermi surface. Okay. And what kind of singularity does that lead you to in the density of states? Textbook answer, 1 over square root e. Okay. But on the BEC side, I'm really just talking about the single band system. It turns out that the Bogoliubov spectrum is like this because the chemical potential has gone outside the band. And now the minimum gap is not delta. It's the minimum gap locus is at k equals 0. The gap value is mu squared plus delta squared under the root. And the density of states in 2D has a jump discontinuity. Okay. And we see all of that when we look at the full multi-band problem. Okay. That in the BEC side, the minimum gap contour is the Fermi energy with 1 over square root e. On the BEC side, just as you enter this, the minimum gap locus is at the gamma point of the zone, and there's a jump discontinuity at the band edges rather than 1 over square root. Now we can go further. Let me not go into the atomic limit because I think it will bore you, but we can solve it. And I'm very happy to tell students who want to learn about it. We can also solve the strong coupling limit and we can do some bosonic Mott insulator to superfluid bosons calculation there. And then in the middle, we can fill up this phase diagram by doing quantum Monte Carlo to show Fermi insulator, Bose insulator, BEC, BCS. Okay, so this is the quantum critical point. These are two crossover lines, and Bose insulator to BEC is actually a phase transition. It should have been marked with a hard line. Okay, so how do we identify the phases in QMC? So of course the insulator is incompressible. Whoops. I'm going back. The insulator is incompressible, so I can calculate the compressibility. and the superconductor is compressible. The superconductor has a phase stiffness which is finite, the insulator has zero phase stiffness, and so you can calculate all these things. How do we get at the gaps? So we can just get them here without analytic continuation by looking at the imaginary time dependence of the Green's function. Remember I told you that the gap would show this weird kink as you go across the superconductor-insulator transition. Simple band gap, BCS delta, and the kink comes about because of the square root of band gap squared plus delta squared. So it's there in their side. So I hope this communicates to you why we trust the numerics even in the other problem. Okay, we look at the pseudo gap, the persistence of the pseudo gap across the superconductor insulator transition. We looked at the minimum gap locus, looked at various other things. So let me just end with this, that this is the picture that comes about. It's a very simple model, and its advantage is you can apply any trick available, analytical or numerical, we get consistent results. The overall story is remarkably similar to the much more complicated story that I talked about in the disorder-driven superconductor insulator transition. But of course, there's no inhomogeneity, there's none of that physics happening. Okay, so there are some, now I want to talk about open problems in the, bigger open problems in the field of superconductor insulator transitions, instead of just talking about are Coulomb interactions important in the disorder-driven transition. Yes, please.
You give some kind of experimental parameter that you can change to standard distribution.
Let's discuss that in private. I have some thoughts, but they're not good enough to be discussed in public. I do have some thoughts. Okay, so in the big picture of things, as I said, there are many superconductor insulator transitions. So a lot of these insulators, in fact, are correlation-driven insulators which have a broken symmetry, like Mott insulators or some other broken symmetry. Okay. So here then the question is, so let's talk about, say, antiferromagnetic. Okay. So then it seems like you could have three possible phase diagrams that either you have two quantum critical points with an intermediate phase in between, absolutely possible. Or these two lines cross, and then depending upon what this parameter is, density or chemical potential, you can either do a Maxwell construction or get two-phase coexistence, but basically you get a first order transition. Okay. The third possibility is that both of these transitions end at a single quantum critical point. This is very unlikely for the following reason. Either this would require nature to be fine-tuned, which it never is, or it would require something very exotic called deconfined quantum criticality, for which we know of few theoretical examples, too few theoretically, and none experimentally. Okay, so I doubt if that. Sorry. And yet, I don't want to get into the details of this, but if you look at underdose cuprates that show superconductivity vanishing at a quantum critical point, and likely some kind of antiferromagnetic order appearing immediately beyond that point. So it seems like a very strange thing it doesn't look like anything on the face of it. It may almost look like this. But actually, I think disorder is playing a very important role in here. And the reason is that in classical critical phenomena, we understand this very well, that disorder can turn first order transitions and make them continuous. There's work of John Cardy and others in simple models, three-state Pot models and so on in two-dimensional shows this. But this is not particularly well studied in quantum problems. But I think this understanding superconductor insulator transitions that occur between a superconductor and a broken symmetry insulator, I think is a very important open area. So why is this important? Because as I told you, cuprates, which have a D-wave superconductor near an antiferromagnetic Mott insulator, and there is evidence of superconductor insulator transitions. That's Ivan Bozovich's data up there, and that's actually from Lemberger's data, and we can discuss why this TC versus DS shows that there's a quantum critical point in there. or magic candle twisted bilayer graphene. In the early days, they labeled this MOT in Pablo's paper. Now we know it's not a MOT insulator, but it has some very interesting broken symmetry structures. And just by changing carrier density, you're going into a superconductor. And actually, disorder is known to be very important. Okay. And most recently, there are data on either few-layer rhombohedral graphene from Long Ju's group at MIT or Andrea Young's group at UCSB, where you see multiple superconducting phases, and they know from the quantum oscillations and the Landau fan degeneracies that these are happening in a half metal or a quarter metal. Now, superconductivity in a quarter metal is ridiculous. What does a quarter metal mean? You have only one spin species, so it has to be triplet superconductivity. Okay, and quarter metal means you have only one valley, which means basically it has to be a FFLO state, because if you are pairing within the same valley spins which are of the same orientation, you have a very strange superconductor. And there's some evidence for chiral superconductivity also. And these same samples actually not only show other broken symmetry phases, which they do, Wigner crystals, but they also show fractional quantum anomalous Hall insulators. So now you have a topologically ordered state very close to a superconductor. And there is this very interesting recent preprint, which shows superconductivity near, again, a topological state quantum anomalous Hall insulator in twisted bilayer multi-telluride. So I think understanding superconductor insulator transitions in these exotic settings is, I think, just wide open game. So I think for the young students, don't feel that there are only some details to be looked at or something. There's just a world out there that if you have understanding of superconductor insulator transitions, you can bring to bear on other problems. Yeah, okay. So let me end with that. Thank you very much.
So just to confirm for Q-press, then the standard phase diagram looks like the AFM first disappears, and after some voting, then.
So it's very unclear. It seems like if you look at MUSR and so on, there are frozen moments all the way until you get to the superconductor. Disorder is playing a definite role there. But this community is geared toward understanding maybe disorder is not driving the quantum, maybe it is, but it's there, and there is likely a broken symmetry other than, but you're right, it's unclear. So like, for instance, if you look at this boson with data, this is clearly a superconductor, but what precisely is this state? I don't think people understand it particularly well. But it could have some kind of antiferromagnetism already in it.
And maybe another related question. So you mentioned that your model in the first part of your talk
yes.
cannot or does not explain the pseudo gap in the field.
Yes, absolutely not. Okay, we can discuss that in great.
Just because U is 0?
No, that is not the reason. The reason is that first of all, there's much going on in the pseudo gap in underdoped cuprates. Okay, there's a proximity to the MOT insulator. Actually, in most materials there's fluctuating CDW order. In a very recent work of Bernhard Keimer's, there may even be long-range CDW order. Okay. The third thing is so there are other orders fluctuating or otherwise present in the normal state. Okay? Not just fluctuating superconductivity. Other thing is the pseudo gap T star is measured in the cuprates as you underdope from variety of probes, angle resolved photo emission, NMR, that's quite high. It becomes very high as you underdope. It goes towards several hundred Kelvin. Whereas if you ask for evidence from fluctuating superconductivity, as for example from say Nernst effect or from finite high frequency measurements of Joe Ornstein, and there's several of them. Those don't go quite up to T star. They go up to several times TC often, but also have a dome-shaped picture as opposed to T star, which seems to be monotonically increasing as you undergo. So I don't think the full pseudo gap can be understood in terms of pairing fluctuations, although there are large regions of the underdome regions where there are pairing fluctuations. Yeah, it's a much more complicated.
I think from Bozovich, they demonstrate for shock noise somehow some freeform polar pairs.
That's right. That is the work not of Bozovich. Maybe the sample was from Bozovich, but Doug Natelson.
Yes, yes.
There seems to be evidence that there may be charged 2E objects in, but the question is, over what doping and temperature range did they show? Yeah. Please.
This is just to understand how the model works. So
which one?
In generally the Hamiltonians that you wrote to find out the phase diagrams.
Okay.
So let's say that we are doing a transport experiment,
right?
And our measurable quantity is resistance or conductance.
Yes.
So is it possible to treat dissipative states within these models in the sense that we can apply a boundary condition saying that the chemical potentials are slightly shifted on two sides, and we want to compute the currents?
So linear response we can do. If you ask me to do nonlinear response, that is asking me to do altogether too much. So here is linear response transport. Because we can calculate current correlations and from that deduce the conductivity or resistivity. But no. And this paper with Mason Swanson et al. In Nandini, there is more on the frequency dependent of the real and imaginary part of sigma of omega also, but that's still linear response. This I'm showing you only this. Yeah, that is.
Question on your second model.
Yes.
So your transition to DC.
Yes.
So you recover, if I understood correctly, you recover the pseudo gap that stays above TC.
Yes.
You recover the energy scales and the phase, sort of phase diagram. The energy boundary got to zero at the yes. So what's specific about disorder in the SIT in your the first model? Since you recovered.
So there, of course, I was driving the phase transition by disorder. I was saying that disorder is going to kill superconductivity.
Yes.
And what kind of localized insulator does it give rise to?
Yeah.
Here I'm saying, okay, I'm done with disorder. I want something simpler. And I'm just changing, if you wish, here the band structure.
Sure. But phenomenology is
similar, surprisingly similar, which we didn't expect. We just started out to answer the question, if you don't have a Fermi surface instability, how will this band insulator become a superconductor? We asked that question. It was a well-posed question. We didn't know where the answer was going to take us. It took us here. That wasn't expected by us or our referees. So,
other questions? Okay. So
I ended early. I think
yes,
everyone is tired, including the speakers. So. Thank you.
Okay, thanks a lot.